Hey, Aaron Topping here. I'm going to be going over my data structure tutorial of the three data structures, the stack, the linked list, and the tree. I did kind of an interconnected project where I wanted all three of them to kind of relate to each other. I'm someone that really struggles a little bit with just like abstract projects. I really like having real world solutions that I can solve. It keeps it interesting, and I think it makes it a little more fun. And so I did something with the movie recommendation system, kind of like Netflix or Apple TV or Plex, which is a server I really like to use with. So the stack is the very first data structure that I put together. I thought this was actually perfect for something that has to do with your watch history. With your watch history, it doesn't have to be any kind of ordered list. You can watch movies in any order as possible. The only thing that really matters is being able to look back exactly in a fixed history that isn't really going to change. And so a stack is kind of a last in, first out data structure. And so I kind of compare it to a stack of plates. If you have a stack of plates on the table, you cannot get to the bottom plate until you take the first stack off, and then the next plate and the next plate. And it's the same thing, the same concept with a watch history and something like that. For movies, you will take them one at a time and go over it. And kind of get this like contiguous list of movies you've watched. There is one challenge though, and one of the things that I kind of put together in the tutorial was, well, if you're popping off that plate or you're popping off that movie, you're kind of losing that piece of information to view the history. And so if you want to view the entire history, how do you write a method to do that? And so I gave them the challenge to do that and then gave them a solution. And it's just as simple as making a temporary stack and copying everything over and then stacking it back on the original stack. It's pretty fun. And I kept the solutions, kind of keep it in the spirit of how we've done it in this class. The next project, or the next data structure, was the linked list. And the linked list I thought was going to be really good for something like a watch list. The watch list is a little different than the history because a watch list would not work in a stack at all, because a watch list is something where you can add things to it, but maybe you want to change the order around. Now, most of the time, you're just going to watch the things on your watch list in order as you added them, because that's why they're there. But what if I came across, say, Dune 2, and I'm like, oh yeah, I want to watch that. And so I add Dune 2 to the watch list, and then I'm like, oh, wait a second, I should probably watch Dune 1 first, and so now I want to add that, and I want to arrange things around. Or maybe I'm looking at my watch list, and I say, you know what, I want to watch this other movie that's at the end and bring it to the front. You can't do that in a stack, but with a linked list, you can, and it's very efficient. And I thought it was just a great tool to use for something like this, where in most cases it's O1 big O notation because you're just kind of looking at the front. But in some cases you go to ON notation because you want to search and traverse down it. But it's kind of like a scavenger hunt where you don't know where all of the pieces, all the nodes are in the memory until, with a scavenger hunt, you have to find this clue to move on to the next clue. You can't go on to the next clue until you find it. It's the same thing with a linked list, is you do it in order. You have to go node to node to node in specific order. And then the final one was the binary search tree. This was probably the most interesting of the data structures. I think it's absolutely critical for something like a large movie database. I mean, if you think of a company like IMDb.com, which probably has hundreds of thousands, if not millions of movies in their database, and people are searching for various filters through the database, it would be really inefficient if every single person had to search in some type of list to find it. But what if you say, what if it was in a logarithmic data structure where we have O log n notation, where every time you're looking for something, it's having the data. So that's how it is with the movie rating system that I have here, where I could build a recommendation system on it, where I can say, hey, I only want the movies that are at least an 8.0 rating or higher. And that's kind of the fun that I had with this is searching the list, finding movies within a specific range, and so on. And so I thought in the context of this data structure that really worked really well for really large databases that had something like a rating system where I could go, well, the lower ratings are on the left side of the tree and the higher ratings are on the right side of the binary search tree. And that's my entire tutorial in data structures, and hope that helps.